Manager at Google Research working on TensorFlow Extended. TensorFlow Extended, or TFX, is Google's end-to-end machine learning platform that powers many of our products. And today, I'll be walking you through each of these components. And I'll also be showing you how you can use the exact same components to design machine learning systems on your own teams. Let's start with a simple block diagram. This orange box represents what people usually think of when I say machine learning. This box contains the ML code, the hyperparameters, the features, and the expertise that goes into designing a high-quality model. However, that's not the full picture, because if you want to run machine learning in production, you have to worry about so much more. You have to think about large-scale data pipelines, making sure your data is clean, making sure your models are safe to be served, and everything else that's on this page. And you may think that you don't need all of this, but I will argue that in the near future, you will. From our experience working with machine learning teams at Google, what is just research and experimentation one day quickly becomes a production service the next. And a problem that fits on a single machine today will require a cluster of machines tomorrow. And because we've run into so many of these problems, scaling up our ML systems at Google, we wanted to build a solution. And that solution is called TFX. TFX is a large platform, consists of many components and services, and it's used widely at Google. And at Google, TFX has had a profound impact on how many teams use TensorFlow, how quickly these teams can go from experimentation into production. And it's been crucial in making Google an AI-first company. And because we know that many of you will run into the same problems when you're scaling up your ML systems, we wanted to open source TFX so that anyone can use it. And so far, we've open sourced these 5 components. So you can go to GitHub today and start playing around with these. And later in this talk, I'll walk you through each of these components and tell you what they are and how you can use them. There's a few things I want to highlight here. The first is that TFX is a real platform designed to solve real problems at scale. And the code that we've open sourced is the exact same code that we run in production. So this is not a side project for our team. And so far, we've released these as individual libraries. So you'll have to use these components individually and make them work together. But we do have end-to-end working examples on GitHub. As I mentioned, TFX is solving real problems, not only at Google, but across Alphabet, which includes companies like DeepMind, Waymo, and X. And TFX also powers many major Google products like Google Search, YouTube, Android, and many more that are not listed here. TFX is also used outside of Google. This is one case study of a healthcare company called Cambia, who use the TFX components, TensorFlow Transform and TensorFlow Server. And by using these components, Cambia allows its data scientists to not have to worry about building and assembling the right infrastructure components, and frees up their time to just focus on developing high-quality models. And that's something that'll benefit all data science and machine learning teams. So let's come back to the TFX diagram. As I mentioned, we've open sourced 5 components, and I'll be walking you through each of these components in order. So the first component of the TFX pipeline is data analysis and validation. We've open sourced this component as TensorFlow data validation. And before we jump into the details, let me explain why data validation is important for machine learning. At a high level, machine learning is this 3-step problem. You start with data, you feed that data into a learning algorithm, and that algorithm outputs some model that hopefully predicts some patterns we see in the data. And so it becomes clear that if we start with bad data, it's unlikely that the output of this process, your model, will be of high quality. So in other words, you put garbage into the system and you get garbage out. And this problem is even more pronounced when you have feedback loops in your system. And this is a very common scenario when you have a model that's serving in production. It's taking real traffic and sending back predictions to users. And then we take those serving logs and train the model on it the next day. And in this kind of continuous training loop, you start with errors in your data. That leads to small errors in your initial model. And these errors propagate and accumulate through this feedback loop, which is something we want to avoid. Let me also give you a concrete example of why this is important. So in this example, we have a model that has a feature called video length. And this feature is measured in hours, so we decide to clip it between 0 and 24. And everything goes well. We train the model, it performs well, and we deploy it into serving. However, a few weeks later, the feature generation code changes. And this might just be because some other team owns this code and they didn't bother to tell us that they changed it. And now this feature is measured in seconds. And all of a sudden, our model starts clipping those videos to 24 seconds. And now this feature is useless and it actively harms the quality of our model. And we end up with a very sad production team. And let me just point out here that this is not a made-up problem. This is actually a situation that happened in a Google production service. And it's impacted the user experience of end users. So the solution to this problem is TensorFlow data validation. And data validation has these 4 parts, and I'll walk you through each of these. The first part is to compute statistics over your data. Let's see how to do this. So let's say we start with some data set and just say that it's 1 day's worth of data. We can use the data validation function to generate statistics, which will analyze the entire data set and generate some important statistics over it. And if you're working in a Python notebook, which is a very common environment for data scientists and developers to explore data and iterate out models, if you're using a Python notebook, you can use our visualization tools to visualize these statistics. And let's see what that looks like. So you'll see if you scroll down, you'll find every feature that was present in your data set. And for each feature, we tell you some important statistics. So for example, we tell you that your drop-off latitude feature is missing in 3% of your data set. We'll also tell you that your tips feature, that is 0 valued for 68% of your data. And maybe this is totally valid, or maybe it indicates some error with your data. And of course, we also give you things like the min and max, the standard deviation. We give you some plots of your features. The next step, after you've computed these statistics, is to use those statistics and generate a schema. And a schema defines the expected bounds of your data. So you start in the same place. You generate some statistics, and you run the infer schema function. And this will infer a schema over your data set. And a schema can be visualized like this table. Again, we have each row as a feature. And we can look at the company feature, for example. It's the second from the bottom. The schema will tell us that this company feature is string valued. It's an optional feature, so it's not required to be present in all of our examples. And it's single valued. This means that it's a single string and not an array or a tensor of strings. And because this is a string value, we also have a domain. And let's see what that domain means. If you scroll down past the schema, you'll get the domain table after the schema. And because the string feature is a categorical feature, we can collect all of the feature values that it takes on in our data set and just put it in one place. That's called the domain. So here, indeed, we see a list of strings, which are taxi cab company names. A few things to note here are that this initial schema is based on a heuristic analysis of your data. So for example, if we notice that 100% of your data set contains this one feature, we'll mark that feature as required. And because these are heuristics, they're not 100% correct. So it's good practice for the data owner to go back and tweak the schema based on their domain knowledge. And the same schema can be used by downstream components like TensorFlow transform. After we've generated a schema that tells us what our data should look like, we can validate data with your schema. One way to validate data is just to visualize it. We can use the same visualization tool as before. It takes in 2 data sets as input, and it will juxtapose the statistics and graphs with it. Let's look at how you might use this. So here, we notice that one data set is half the size of the other. So we change the graph to display percentages. And then we can expand the graph to take up the entire page. We notice that the distributions still look a little bit different between the two data sets. So we can switch the view of the graph. We're now looking at quantiles. And what we see is that the distribution is actually pretty much the same. It just looked different in the histogram because there are more outliers in one data set. So this is good. Beyond just visual inspection, you can also programmatically validate your data with the validate statistics function. This function takes in your data set as well as the schema and tells you if you have any examples in your data set that don't match the schema and returns these as anomalies. This function also takes in 2 data sets as input, and it'll track if there's any distributional differences between the 2 data sets. So even though 2 data sets may conform to the same schema, they might be distributed differently, and this is something that you might want to look into. You can also visualize the anomalies, and let's zoom into this. So here, we tell you we saw an unexpected string value for this feature, and we tell you what that value was. And there's 2 things you could do from here. One, this might actually just indicate some valid values that you want to include in your data set. And so you can just update the schema to include these values. On the other hand, if you have anomalies, this might also indicate that you have errors in your data generation pipeline. And so that's something that your team will want to look into. The final step is detecting training serving skew. And to do this, we can use the exact same validate statistics function, but in a serving environment. And this means it will look at your serving logs and make sure that there's no distributional differences between the data that you're getting in from real users and the data that you've been training on. If there are differences, this is a source of training serving skew, and it will harm the performance of your model. So it's something you want to watch out for. I'll just wrap up with some statistics of data validation. Data validation is the most popular TFX component. It's used by hundreds of product teams throughout Google, and some teams set up a TFX pipeline just to use this component. And it serves petabytes of training and serving data per day, so it's built for very large-scale problems. And we've also documented many machine learning wins by detecting these data anomalies, both in existing systems and new ones. So that's TensorFlow data validation. You can find it on our TensorFlow GitHub account. So now that we've validated that our data is good, the next step is to transform it and feature engineer it. And that step is data transformation. And we've open sourced this component as TensorFlow Transform. So TensorFlow Transform is a library that allows you to express data transformations as TensorFlow graphs. And it also uses Beam behind the scenes to calculate exact statistics over your entire data set. And Beam is an open source library that allows you to build large-scale data pipelines. And let me give you a concrete example of why this is useful. A common transformation for numeric features is mean normalization. And what this means is that you take a numeric feature and you subtract the mean and you divide by the standard deviation. And both these values, the mean and the standard deviation, they require a full pass over your entire data set to calculate. And if your data fits into memory, this is pretty trivial. You can just call a NumPy function. But for large data sets that we see in the wild, this becomes much harder. And TF Transform will handle this for you out of the box with utility functions like scale to z-score that does mean normalization. Things also get complicated when you want to do transforms of transforms. And TF Transform will handle this use case as well out of the box. The output of TensorFlow Transform is a static TensorFlow graph. This is your transform graph. And we inject the output of the statistics computations as constant tensors into this graph. So now we have a hermetic transform graph that can repeatedly apply the same transformation over and over again in different environments. So in training, we can use the transform graph to convert our raw data into features that we train on. And in serving, we can use the exact same transform graph to make sure our model is serving on the same features that it was trained on, and have one source of truth for our feature transformations. The way you use TF transform is by defining a pre-processing function. This function takes in your raw data as input, and you'll iterate over the features in your raw data. For each feature, you might call some TF transform function. The first one here is scale to z-score, which we've talked about. The second is string to int. So this will look at your entire data set, calculate a vocabulary for your string feature, and use that vocabulary to convert string values into integer IDs. The third example is bucketize. This is another transformation that requires a full pass over your data set to compute the boundaries of the buckets that you want to sort values into. Here's some more common use cases. We've talked about scaling, we've talked about bucketization. For text features, a common transformation is computing n-grams over your text. And this transformation on the bottom is really interesting. You can actually use TF transform to apply another TensorFlow model to your data. So for example, if you have raw image data as one of your, in your data set, you can use transform to apply an inception network to that raw image data, and then use the output of that network as just one feature that your model is actually trained on. This is really powerful because it allows you to reuse existing models. I think the clicker is out of battery. I can also use the laptop. Okay, that works. Thanks. Okay, so that was TensorFlow transform, and you can find out more about it on GitHub. So after we've transformed our data into features, the next step is to build a model that can use these features to train on. And the component that houses the model in TFX is called the trainer. And the way you build models in TensorFlow is by using the Keras or the estimator APIs. Let's start with TensorFlow estimators. This code snippet shows you how to use canned estimators in TensorFlow. And canned estimators are just predefined machine learning algorithms that work out of the box. So in this example, we are defining a DNN linear combined model. And this is a model that combines both a neural network and a linear model into one, which gives you the best of both worlds. We also call this a wide and deep model. Now, this is a fairly complex model architecture. So if you were to wire this up from scratch, it would take a lot of care, be somewhat difficult. Luckily, since it's a canned estimator, we can just build it in one line and start training on it the next line. It's a very simple API. And TensorFlow Core has these four canned estimators. You'll find deep neural network models, linear models, DNN linear combined models, as well as boosted tree models. And if you look in tf.contrib, or if you just search GitHub for estimators, you'll find that most common machine learning algorithms have already been implemented as canned estimators. So after training, you can save your model with its learned weights into a saved model format. And this saved model format is the standard format that all TFX components uses. A saved model contains the weights and the graphs for training, eval, and inference. So you can directly pass that saved model into downstream components like model analysis and serving. If you use Keras, it's the same story. Keras is a popular API used to define deep layered models. So you build your model, you train it, and then you export it as a saved model. The same format that you can use in other components. So after you have a model and you've trained it, the next step is to evaluate how the model performs. The way we do this is with TensorFlow model analysis. So we take the same saved model that we just got, and we run model analysis on that saved model. And model analysis will compute sliced metrics at scale. And what does that mean? It means that we use Apache Beam to run over your entire evaluation data set to compute exact metrics that can be sliced. And these are different than the metrics you see in TensorBoard, because TensorBoard outputs approximate metrics that are based on mini batches. And those are outputted at specific intervals during training. On the other hand, model analysis takes an already trained model and allows you to do some very deep analysis on it. And to highlight what I mean by sliced metrics, let me first show you an example that's not sliced. So here, we just run the run model analysis function. We let that finish, and we can visualize the results in a Python notebook. Visualization looks like this. We have a few knobs at the top, we have a graph, and then we have a table at the bottom. And this table will show you some metrics that you're probably familiar with, like accuracy, AUC score, the loss. And what does this tell us? It tells us that, on average, our model does pretty good. It has 95% accuracy. But it doesn't tell us that, it doesn't tell us how well our model performs on specific slices of our data set. So maybe our model underperforms for specific feature values or for specific slices of the population. Those kinds of things are hard to tell from this aggregate metric. So the solution to this is to slice our metrics based on feature columns. So at the very top here, we tell model analysis we want to slice our metrics on this feature column called trip start hour. We wrap that feature column in a slice spec. We pass that slice spec to all of the model analysis functions. And just so you have some context about what this feature means, we're using the Chicago taxi data set as an example here. And this data set contains millions and millions of taxi rides. And a feature for a taxi ride would be when the trip started. So that's the trip start hour. We also have features like the fare that the passenger paid, the pickup and drop off locations. And the label in this case, the thing we're trying to predict, is how much the passenger tips the driver. So we want to slice our metrics based on when the trip started. We run the same model analysis functions, and we get a more detailed output. So here, we say we want buckets of size 100. We want to look at the AUC metric. And now notice that all of the AUC metrics are displayed for each slice. And this will allow us to identify if one slice is underperforming the others. If we wait for this to loop around again, we'll see that the lowest performing slice is actually the trips that start at 2 a.m. And what does this mean? This might tell us that we have bad data for trips that start at 2 a.m. This might tell us that we don't have enough data for trips that start at 2 a.m. Or this might just say that there's more natural variability in trips that start at 2 a.m. And in any case, knowing this about your data will help your team debug the failure modes of your model and see if it's fit to run in production. TFMA model analysis also provides some common plots that work out of the box. We have a calibration plot that shows you your labels plotted against the predictions. We have a prediction distribution plot, precision recall curve, and an ROC curve. And note that these graphs are calculated based on the entire eval data set. But as you can expect, you can also slice these graphs down to specific features and feature values. The last feature I'll highlight here is you can use model analysis to visualize a time series of models. So if you have a continuous training pipeline that trains a new model every day, you can plot all of those models here and see that your accuracy rate, your AUC score, is going up or trending downwards over time. That was model analysis. So after we've confirmed that our model is performing well for all the slices that we care about, the next step is to push that model into survey. And the way we do that in TensorFlow is with TensorFlow survey. So we take the same safe model that we had from before, and we can launch a server that's hosting our model in one command at your terminal. You run the model server command. You point to where your saved model is on disk. You tell it the name of your model, the port you want the server to run on, and you have a model that's ready to serve requests on the server. Once your server is up, you can send requests to it with gRPC. If you're familiar with gRPC, this is a straightforward code snippet that shows you how to construct an example and then send a request to your model server. But we know that not everyone uses gRPC, and in fact, one of the top requests on GitHub was for a REST API. So I'm very happy to say that our model server now supports both a REST and a gRPC endpoint with the same API. So you can classify, predict, and do regression. The way you launch the model server with a REST API is just with the command line flag for the REST port. And once that's up, you can just curl post requests to your model and get responses back. So here, notice that we've encoded our example as just idiomatic JSON. And the result we get back is probabilities of each of the label classes. So that was TensorFlow survey. And that was a lot.